Kia ora, Year 11, 12 and 13. This is a Conics question from the 2008 Scholarship Calculus paper, and it's one that we're looking at Cole in session 20 on conic sections, but it's got a lot of little places that you can go wrong, so I thought it was worth videoing. So let's slowly work through the question first and then just see what clues we've got for what we need to do. It's one of these ones where it's reasonably obvious what each next step is. The challenge in here is in not mucking up the algebra and in trying to see the big picture and not getting lost in the detail. So we're given a curve. We're not told what it is, but we're told it's got the following parametric equations, and it's got x is equal to sec theta minus 1 and y is equal to 2 tan theta plus 2. So if you look at your formula sheet, you can probably figure out which of the three main curves it is. Is it an ellipse, a parabola, or a hyperbola? And this is the angle, and so this angle feeds into both the x and the y values. And we have a choice in this question about whether we stick with the parametric form or whether we work more with the Cartesian form. But the very first thing we have to do is to find the Cartesian equation of the curve. So let's start by just writing out the two things and seeing what we might do. So we've got x is equal to sec theta minus 1 and y is equal to 2 tan theta plus 2. So my goal is to get rid of the trig in there and just have x's and y's. One of the things that's going to be useful are our trig identities. And whenever you've got a conics problem and you have to move from parametric to Cartesian, the best place to start is with the Pythagoras identity. So that's your first little clue. So the shorthand way of writing that is sine squared plus cos squared is equal to 1. Of course, you're given this on the formula sheet, but I usually just derive it. And in this case, we're working with sec and tan. So the one that we want is sec squared theta minus tan squared theta is equal to 1. Now that suggests to me that if I do something here so that I can start squaring both sides, I might be able to manipulate it into this form, and that's what we're going to do. So first we'll get x plus 1 is equal to sec theta, and then y minus 2 divided by 2 is equal to tan theta. Now if I square both sides, I can go straight to writing down the Pythagoras identity, which is sec squared minus tan squared theta is equal to x plus 1 squared minus y minus 2 on 2 squared, and we know that that equals 1. So we have straight away got the equation of a hyperbola. So we can dive into the rest of the question, or we can just take a moment to look at roughly what shape that is and what we're being asked to find. Now, I've done that in GeoGebra. You don't have the luxury of GeoGebra in the exam, but you do have your graphics calculator. So let's see what we've got in the question. So we've found the Cartesian equation of the curve, and it's a hyperbola. And we know from looking at it that the center of that hyperbola is going to be at -1, 2, and the A and the B are telling me something about the steepness of the asymptotes. But because most of you watching haven't done much with conic sections, this is probably going to feel a little bit tricky. So here's what the graph looks like. Where are we? So this is the basic graph that we've got. This is the equation of x plus 1 squared minus y minus 2 over 2 squared is equal to 1. And you can see the center is sitting in here at -1, 2. And the asymptotes here relate to the A and the B. So 2 over 1 is going to be the slope, plus or minus 2 over 1 is going to be the slope of those asymptotes. I'm not going to go through all of that now, and you don't need it for this question. But remember that Khan Academy's definitely got some good stuff on conics, and I think Education Perfect has as well, and the Delta book is fantastic on them. So now let's see what we're asked to do. Right, so we've done the easy bit. I think that was worth 1 or 2 marks. And now we're going to look at the next part, where we're talking about a normal at the point P. So the normal at the point P, which is where theta is equal to pi on 4, meets the curve again at the point Q, in the region where x is negative. Find the y-coordinate of Q in the form a over b, where a and b are integers. Okay, so let's draw just make some room here. We're going to draw a bad version of that hyperbola, the kind of sketch you'd do if you were in a big hurry in an exam. So here are my axes. Here's my centre. Let's whack some asymptotes in. Okay, so here's one hyperbola, here's the other, right? Terrible picture, but that's okay. We're looking for a point on that curve, and that point might be here. And we want the normal at that point. So here's the tangent, and the normal is going to go through like that. And it's going to meet this curve somewhere over here. And what we have to do is to find the y-coordinate of this point over here. So this is point Q. This is point P. What I want you to see from this is that even though that sketch is really, really terrible, it still tells me exactly what steps I need to take in this question. Okay, so step 1 is going to be to find point P and to get the coordinates. Step 2 is going to be to get the normal equation, right? And we'll probably use y minus y1 equals mx minus x1 to do that. Okay, and then we need to find the intersection of two things, the intersection of that line, of the normal line, and the curve. So what we're looking for in the end is that big blobby mess of point Q, and we have to just find the y-coordinate of it. So I'm just going to set off on those 3 steps now, but if you keep that diagram in mind, I think it's going to help. Okay, so where do I start? Well, you can, to find the equation of the normal, we're going to need to find the gradient of the tangent first. So there are 2 ways to do this. You can do it using parametric differentiation, but I just got on with it from my Cartesian equation, which was this. And so we can differentiate this with respect to x. So I'm going to use implicit, which I think comes up in almost every scholarship paper. So here it is in this one. That should say 1 up there. That should say 1 there. And then when I differentiate 1 with respect to x, I get 0. Now we have to clean this up. And you have to watch out with this question that you don't make small algebraic mistakes. So I've got -2 times x plus 1. Right, now finally, that gives me dy by dx, the gradient of the tangent, as this. Now I haven't even bothered to simplify that fraction, but I'm going to do that now. So this goes, and I'm left with 4 times x plus 1 over y minus 2. That means that the gradient of the normal will be the negative reciprocal of that. So that's going to be 2 minus y over 4 times x plus 1. So far, so good. So what's the next thing we've got to do? Let's go back to the question again. I'll just keep on going back and having a look. Right, so we've found the gradient of the curve. We need to find point P, right? And so we've got to start working in theta equals pi on 4. So when theta equals pi on 4, we have x is equal to sec theta minus 1, which is 1 over cos of pi on 4 minus 1. Cos of pi on 4 is 1 on root 2, so this becomes root 2 minus 1. Now what was y? Well, y was 2 tan pi on 4 plus 2. Tan of pi on 4 is just 1, so 2 plus 2 is 4. So we've got the coordinates of point P. Now it's got a certain there, but it's not too bad. Because remember, we're asked to give our answer with a and b in integer form, so we don't want any horrible decimal approximations. But this is scholarship, so we don't want to do that anyway. Right, now, what we want to do now, we've got the x and y values, so I can sub those in and get the gradient of the normal. So m normal is equal to 2 minus y, so 2 minus 4 over 4 times x plus 1. So root 2 minus 1 plus 1. So it's not too bad. I've got -2 over 4 root 2, which is -1 over 2 root 2. Finally, we're good to find the equation of the normal. Right, you can hear the paper rustling because I've pre-written this one. I'm not just doing this one as I go because there are so many places to go wrong. So we've got y minus y1, 4, is equal to m, negative 1 on 2 root 2, times x minus x1. So that gives me minus root 2 minus 1. X minus root 2 plus 1. Cleaning that up, I get y minus 4 is equal to, what am I going to do here? So I'm going to be a little bit smart about this step for once. I'm going to do x plus 1 minus root 2. So I'm looking ahead when I do that because I know where I'm going from the start of the question, which is that I want to get the normal equation and then I want to substitute, or find the intersection of the normal and the curve. So if you look at what the curve has got, this is the curve and it's got x plus 1 in there. And I want to end up getting the y coordinate, so I don't want to have any x's in. So I'm going to be trying to take this and get rid of it with stuff that's got y's. So that means that I'm not looking to make x the subject, but I'm good if I can just work with the x plus 1. And you can see the x plus 1 is sitting in here. So that's a very long way of saying that have a look before you start wildly expanding things out. I'm going to leave that like that. And then I'm going to have plus root 2 on 2 root 2. And this simplifies so that I can now get y minus 4 minus 1/2 is equal to this. So I've got y minus 9 over 2 is equal to negative 1 over 2 root 2 times x plus 1. And we're trying to substitute this into the equation. So the next step is to say, well, 2 root 2 times y minus 9 over 2 is equal to negative x plus 1. Or negative 2 root 2 times all of that. I'm going to run out of time, I think. This video is only allowed to be 15 minutes, or I don't know what happens. So squaring both sides gives me root 8. Let's see. 2 root 2 is root 8. So we get 8 times y minus 9 over 2 squared is equal to x plus 1 squared, I think. Yep, that looks good to me. So now we're ready to sub that in to my main equation. So remember we had x plus 1 squared minus y minus 2 squared on 4 is equal to 1. We get 8 times y minus 9 over 2 squared minus this. So now we're down to really easy maths that we don't want to muck up. Multiplying everything through by 4 gives me this. And then I form a quadratic. Finally, we get this. I'm going to skip a tiny bit of working out. We get down to this quadratic, and we know that one of the solutions is y equals 4. So we can factorize really easily like this. We can try this and see if it works. We've got y minus 4. We must have 31y squared. We know there are integer solutions here, or there's a fraction solution. And now here I'm going to have minus, well, 4 watts of 640, 160 equals 0. So there you go. This works. We get 31y squared minus 131y squared minus 124y minus 160y, which works to give me that, plus 640. So my last solution, I get y equals 4 or y equals 160 over 31, giving me A is 160 and B is equal to 31. There you go. I've got 25 seconds to spare to talk about it, and I'm just going to quickly show you a picture of it done nicely in GeoGebra as a reward for watching to the end. Also a pineapple lump. Come and claim it. I promise I will buy some. So that's my first picture. And then this is my second picture. So look what we found. It matches beautifully. That's my point. And then this is point Q up here. And you can see, if you look at that, that the y coordinate is indeed 160 over 31. Okay, so do that on your graphics calculator and do this question again to make sure you can do it. Thanks for watching.